Welcome to the training for the new production scheduling cloud application. This is number 8 out of 12 presentations. In this lesson, we will first discuss schedule stability, why it is important, and how usage of a fixed time fence can help increase schedule stability. Further, we take a closer look at how the schedule horizon start and fixed time fence are determined based on different schedule option settings. We conclude the lesson describing how manual schedule changes are implemented. Let's start with schedule stability. We already discussed the key tasks in a production scheduling cycle in previous lessons. We know that the goal of the production scheduling process is to generate a good and executable schedule, and by doing so to add value to the enterprise. It immediately is clear that the value that a schedule provides diminishes the more shop floor execution deviates from that schedule. Short-term changes cause disruption on the shop floor. They often require additional setups and may lead to having to expedite materials. Some short-term changes cannot be avoided and simply must be dealt with, for example, equipment breakdowns or material issues. But the scheduling process itself should not contribute to schedule nervousness. Instead, it should help increase schedule stability. And this can be accomplished by using a fixed time fence. Let's have a look at the business problem of generating a production schedule across multiple scheduling cycles. Assume that we are currently in scheduling cycle N. The scheduler has generated a schedule, then analyzes and manually adjusts the schedule. Once satisfied with the schedule, the scheduler releases it to execution. On the shop floor, the schedule is then implemented. However, there may be deviations, with some operations being performed faster or slower than scheduled, or they are started a bit earlier or a bit later. In addition, there might be break-ins, meaning work orders were executed that had not been scheduled at all, and the other way around. There could be work orders that were scheduled, but that have not been started yet. Therefore, the starting point for a new scheduling cycle N+1 is generally slightly different from the schedule that was published in the previous cycle N. Now let's look at the next scheduling cycle N+1. Clearly, the work order operations that are currently being worked on should be completed. But after these operations are done, the question is, what should be worked on next? And this leads to the question of how to create a new schedule. One approach is to simply keep the old schedule and add new work orders to the end. This, though, may not be wise, since any new hotter work orders would never be inserted in an earlier position. Another approach is to recalculate the whole horizon after the currently running operations. This approach likely increases schedule nervousness. And a reasonable compromise is to keep a portion of the previous schedule and to freely recalculate only the horizon after such portion. And this can be accomplished via the usage of a fixed time fence. The work orders that are scheduled to start inside the fixed time fence will be placed as they were scheduled previously. And this contributes to increased schedule stability in this earlier portion of the horizon. Outside the fixed time fence, though, the schedule is recalculated. New work orders are inserted and operations are resequenced and may be offloaded to an alternate resource as beneficial. At the end of scheduling cycle N+1, the schedule can again be released to execution and the process repeats itself in the next cycle. So in this example, We kept the front portion of the schedule stable while allowing schedule flexibility to accommodate and consider new work orders further out. Now in the next topic, we will discuss the different fixed time fence options that production scheduling enables. The fixed time fence in production scheduling is defined in the schedule options, and its consideration is as follows. Inside the fixed time fence, only firm work orders and work orders in released status will be scheduled. Automatic scheduling does not re-optimize in the fixed time fence. Instead, the work orders are scheduled as per their dates in execution. Now, outside the fixed time fence, automatic scheduling has complete flexibility to reschedule and re-optimize. However, manual schedule changes are always possible throughout the whole horizon. Production scheduling allows defining a fixed time fence in two distinct ways to address different customer needs. This is controlled via a schedule option horizon extension. If horizon extension is set to rolling, then the fixed time fence is always constant in length. But if the horizon extension is set to dynamic, then the fixed time fence varies in length, depending on the current day of the week. This is for customers who intend to form their schedule, for example, every Thursday until the end of the subsequent week. And as time progresses, the fixed time fence shrinks day by day until the next Thursday is reached, at which time it is extended again. So now let's go over a few details. Let's have a closer look at how the fixed time fence is determined when horizon extension is set to rolling. In addition to schedule option horizon extension, fixed time fence in days and anchor date and time are relevant. The fixed time fence is then determined as follows. First, consider only the time portion of the anchor date and time field, which in this example is 12 a.m. The date portion is irrelevant. Then the schedule horizon start is determined as the previous occurrence of that anchor time ahead of the current schedule refresh time. The start of the fixed time fence will be equal to the schedule horizon start. And the end of the fixed time fence is simply determined by adding the fixed time fence in days value to the start time. Now we will look at a couple examples. So in this example, the fixed time fence in days is set to 7 days and horizon extension is rolling. With the time component of schedule option anchor date and time being 12 a.m., the schedule horizon start and the fixed time fence start is always 12 a.m. ahead of the schedule refresh time on the current day. And the current day is indicated by the green bar, and the start time is indicated by the black diamond. The fixed time fence then always spans 7 days from that start time and is independent of the day of the week. And here is indicated with the red bar. Let's look at another example where the time component of anchor date and time is not midnight, but for example, 8 a.m. There are two cases to consider. Running a schedule refresh before 8 a.m. on a given day or after 8 a.m. on a given day. If the refresh is run sometime after 8 a.m. on a day, then the horizon start and fixed time fence start is set to the current day at 8 a.m. And the fixed time fence spans 7 days from that time onwards. Now, if a schedule refresh is run sometime before 8 a.m. on a given day. Then the horizon start and fixed time fence start is set to the previous day at 8 a.m. And same as before, the fixed time fence is 7 days from that time onwards. If horizon extension is dynamic, then additional schedule options are relevant, namely the fixed time fence minimum in days and the fixed time fence extension in days. The schedule horizon start and fixed time fence are then determined as follows. Here we now consider both the weekday and the time portion of the anchor date and time. Note we consider the weekday, not the actual date. In the example, April the 20th, 2020 is a Monday and the time is 12 a.m. We set the schedule horizon start as the previous occurrence of that anchor time ahead of the current schedule refresh time. So again, here it is 12 a.m. of the current day. The fixed time fence start is the previous occurrence of the anchor day of the week and that time ahead of current schedule refresh time. Here, this is the previous Monday at 12 a.m. And the fixed time fence end is then determined by adding the fixed time fence in days to the fixed time fence start. This results in a fixed time fence end as the subsequent Monday at 12 a.m. Next, the effective fixed time fence is determined, which is the portion of the fixed time fence that is after the schedule horizon start. And if this effective fixed time fence is less than the fixed time fence minimum, then a fixed time fence extension is added to it. Note that if the fixed time fence is not a multiple of 7 days, meaning full weeks, then depending on the other values, there could be constellations where after applying above logic, the fixed time fence is still less than the fixed time fence minimum. In such cases, production scheduling will simply extend the fixed time fence to meet the minimum. Let's again review an example. Here, the fixed time fence is 7 days, fixed time fence minimum is 4 days, and the extension is 7 days. Anchor day and time are Monday at 12 a.m. The first scheduling cycle shown here has a schedule refresh occurring sometime on a Wednesday. So the schedule horizon start is set to 12 a.m. of that Wednesday. The fixed time fence start is the previous Monday at 12 a.m. indicated via the yellow diamond. Adding the 7 days fixed time fence results in an effective fixed time fence of 5 days, shown in red. This now is greater than the fixed time fence minimum of 4 days, so no further action is necessary. Let's assume the next scheduling cycle has a schedule refresh time occurring sometime on the Friday. The schedule horizon start again is set to the 12 a.m. time of that Friday. It's the black diamond. And the fixed time fence start is again the previous Monday at 12 a.m. Adding the 7 days fixed time fence results in an effective fixed time fence of just 3 days, shown in red again. This is less than the fixed time fence minimum of 4 days, which requires increasing the fixed time fence by adding the fixed time fence extension of 7 days, resulting in a 10-day fixed time fence. And the last scheduling cycle shown here is analogous to the previous one. The effective fixed time fence is initially only 2 days, and the extension is again required, resulting in a 9-day fixed time fence. Here is another example for dynamic horizon extension. The intention here is to form the schedule every Thursday to the end of the second subsequent week. The calculations are performed in analogous manner to the previous example. Key is the determination of the schedule horizon start, and the fixed time fence indicated by the yellow bar, and the effective fixed time fence, which is shown via the red bar. If the effective fixed time fence is less than the fixed time fence minimum, then the fixed time fence extension is added. Now, the last topic of this lesson is concerned with manual scheduling. Manual scheduling is performed as part of the analyze and adjust step of the production scheduling cycle. There are different reasons that warrant the use of manual scheduling. First, the scheduler may have additional intelligence not contained in the schedule data. Second, there could be execution issues that require schedule adjustments. And finally, the use of heuristics in the application when calculating the schedule naturally results in schedules that may be improved locally by the user. The different means to manually adjust the schedule were already explained in lesson 6. In the Gantt chart, work order operations can be moved to a different point in time or to an alternate resource using drag and drop. In the dispatch list, the user can edit operation start times or resequence the work order operations. Now, in all these cases, a repair must be started to ensure that the desired changes are indeed implemented and propagated. In addition, the repair will ensure that the step dependencies within a work order routing are respected. Note that editing down calendar events in the Gantt chart and using the need by override in the dispatch list are other possible changes. Those, though, require a solve, not a repair. The question, what does the schedule repair do, directly leads to the question, what does the repair not do? The repair aims to implement the desired manual schedule changes without disrupting other areas of the schedule. To achieve this, the repair does not look for opportunistic improvements, but focuses only on the localized schedule changes entered by the user. And to enable that, the repair relaxes resource capacity, resource availability, and inventory constraints. So consequently, it is up to the scheduler to ensure that the manual schedule changes overall result in an executable schedule. In the following demonstration, we will have a look at a few of the options we discussed, see how they impact the fixed time fence, and perform some manual scheduling actions. Now let's look at this specific schedule. In section Schedule Parameters in the Manage Schedule Options page, we can specify the fixed time fence in days, which here is set to 3 days, as well as the horizon extension, which we have here as rolling, which means the start date of the schedule as well as the start date and time of the fixed time fence. They're independent of the current day of the week. They roll forward with every day, and they will simply be anchored at the previous occurrence of this time in the anchor date and time field. Using this flag, we can control whether released work orders that currently are scheduled to begin inside that fixed time fence period will be formed in case they are not yet formed. to enable them to be scheduled inside the fixed time fence. Only form work orders can be scheduled inside the fixed time fence. Everything else will be outside the fixed time fence. I just ran a refresh and solve, meaning I retrieved the current data from SCM execution and regenerated a solution, a schedule. If we look at that, because it's solved, it actually re-optimized, picked resources, established sequences, considering capacity constraints, and so on. We observe that this gray line is right after 3 days of the start of the horizon, and it indicates the end of the fixed time fence. Highlighting form work order operations shows that only form ones are actually scheduled inside that fixed time fence. Of course, I could manually drag operations into it. For example, let's just say, well, this is a super urgent job. I'm gonna move that right into the beginning of the fixed time fence, right in the beginning of the current day. That is one action I can do. And if I repair, then we will see that this change will be implemented. I'll take a brief moment. It's completed. And now you see that Volg or operation that is not form was manually inserted into the fixed time fence. So this is possible. However, the automatic schedule generation will never do that. So that was a drag and drop operation. And of course, a drag and drop goes not only on the same resource, but it can be across resources. I could go ahead and move this operation up here. And I should really always run a repair after every single manual schedule change. But right now, I will just go ahead and show another one before doing so. Let's pick the injection molding resources. And to actually guide me in what change might be a reasonable one, let's look at some of the attributes. So with respect to a good change, let's maybe look at a resequencing move where I say I want to move this operation back here to be in line or in a run with the other, green color operations, which corresponds to their specific attribute values that they have. So I find that operation, it's here. Using the arrows, I can move it back. And now I can initiate a repair solve. However, to just demonstrate yet another schedule change, I could maybe go ahead and I move this operation a touch back by editing the start time. Let's say I'm gonna only start that an hour later. Okay. Now I will perform the repair solve. And again, right now I have several changes that are being implemented with that repair solve. And that is actually not advisable. Typically, you want to implement one change at a time. Another observation here is that resequencing ensures that all the operations that are part of the resequencing in the dispatch list are spread out, meaning that they are adjacent to one another and overlaps are avoided. Dragging and dropping and editing start and end times, however, do not ensure that. So this is something that has to be resolved then afterwards, if necessary. And one way to resolve it actually is as follows. I can select that operation up here. Again, I select it in the, here in the dispatch list. And then I make sure that I select all the other operations by holding the Shift key down. And now I perform the notion of a quick drag and drop. And this now, when I repair it, will ensure that the operations are again spread out so that they don't overlap, that they will be adjacent to one another. Let's wait for the solve results. Okay, so they're now not overlapping anymore, they are spread out. So this is a way to resolve overlapping conflicts that get possibly created by drag and drop and or um, editing the start and end time in the dispatch list. So in summary, um, this lesson covered how we achieve schedule stability using a fixed time fence, and also how a fixed time fence is determined in specific situations using horizon extension rolling and dynamic. And we also touched on various manual schedule changes that require a repair solve, what the repair solve does, and what it does not do. And we've seen some of those in this brief demonstration.